All right, going to be working number 17 from 12.6, which is triple integrals in cylindrical coordinates. So we're asked to evaluate the triple integral over the region E of the square root of x squared plus y squared with respect to volume, where E is the region that lies inside the cylinder x squared plus y squared equals 16, and between the planes z equals -5 and z equals 4. That's pretty straightforward here. So if I try and draw the region E, it's a cylinder, radius 4, and it opens up through the z-axis. So it's going to go like this, it's going to go down like that. It's going to have a radius of 4. So it hits here at 4, it hits here at 4 on the x and y axes. And then I'm going to enclose this thing with two other planes, z equals 4 and z equals -5. So z equals -5 is just a flat sheet that's been moved down. It's the xy plane moved down 5, and then I have another sheet up here which is going to cap off the top of the cylinder. So we got a pretty easy region E here. It's that right there. Now, if we try and look at the projection of this onto the xy plane, so we can see kind of what I've referred to as the shadow, but it's really just, it's going to create, where this object goes through the xy plane is going to create our region of integration. And that is going to be somewhere in here, like this, which is this circle on the ground here, right? So I need to find the top cap, the bottom cap of this. So the top is pretty straightforward, z equals 4, and then z equals -5. So this is my u2 of xy equals 4, my u1 of xy equals -5. But my region of integration, okay, in two-dimensional space, my region of integration in the xy plane is a circle radius 4. So this is perfectly suited here for a polar region. So I'm going to convert this from Cartesian to cylindrical, which is basically polar. Excuse me, my allergies are really bothering me today. All right, so let's describe this region. Theta is going to be between 0 and 2 pi. My radius is going to be between 0 and 4. And then my z values are stuck between, so I'm looking at the caps here, -5 and 4. And so I'm going to now convert this triple integral over to the cylindrical coordinates. And these are all constants, so I can change the order of integration, but I'm going to go this way and go remember, because I'm going to cylindrical, I need an r in the integral, and then dz, dr, d theta. And the outer one, 0 to 2 pi. The middle one, 0 to 4, that's r. And then z restrictions, -5 to 4. And I'm integrating this, but again, going to cylindrical, I use the same conversions as I did in polar. So remember, x squared plus y squared is r squared. Square root of r squared is r, so I just have r right there. And that's it. This is r squared. And now I'll do my integration. So 0 to 2 pi, 0 to 4. Antiderivative of r squared is 1/3 r cubed. 1/3 r cubed. And I'm going from r equals -5 to r equals 4. Oh, hold on. Oops. Integrating with respect to z first. R squared z, antiderivative of that with respect to z is z. Z is going from -5 to 4. Then dr d theta. So, let me give myself some room here. So we have that equals the integral from 0 to 2 pi. And the integral from 0 to 4. And now let's plug in 4 for z. I get 4r squared. Let me write that down. Plug in 4 for z, I get 4r squared. Minus, now I plug in -5, I get -5r squared. Dr d theta. So that's going to give me 9r squared. Now I'm going to do this integral. Antiderivative of 9r squared, you have to do the 1/3 thing. So you're going to get integral 0 to 2 pi, let's see, 3r cubed from r equals 0 to 4 d theta. And then plugging in 4 and then plugging in 0. When you plug in 0, it all goes away. So you're just going to get integral 0 to 2 pi. And then, let's see here, 4 times 4, 16 times 4 is 64. 64 times 3, 180, 192. So you get 192 minus, of course, 0 d theta. And the antiderivative of 192 with respect to theta is just 192 theta. Theta going from 0 to 2 pi, which is what? 384 pi. Let's see, number 17. Okay, that's it. All right, let's move on and do number 18. Is evaluate the triple integral over E of z dv, where E is enclosed by the paraboloid z equals x squared plus y squared, and the plane z equals 4. So I'll try and draw that region over here. Okay, z equals x squared plus y squared looks like a bowl. Of course, it keeps going up forever and ever. And then z equals 4 is just a plane parallel to the xy plane up here. Just cuts off my paraboloid. So our region E should look like this. It should be this solid here. Now, what we need to determine is what the top of this surface is, or top of this solid is in the bottom. Well, the top of the solid is just z equals 4, but the bottom of it is actually the paraboloid. So it's this piece, which is z equals x squared plus y squared, that. And we still need to figure out what the projection of this solid down onto the ground is. So we want to know if we project this down onto the xy plane, what we're going to get. So that projection, down here like this, creates some region on the ground. Well, it's obvious, I think, from the picture it's going to be a circle. It's just a question of how big is this circle. So it's just this circle up here moved down. So it's where this plane cuts through my paraboloid. So what I want to know is when do these two meet each other, right? So I just set them equal to each other. I get, sorry, no z. I'm going to set the first one, this one equal to this one, so I get x squared plus y squared must be 4. So I know that that looks like this radius 2, and this is my region on the ground here. So I know it hits here at 2, 2. All right, and that's perfect for conversion over to polar, which means this is going to be a cylindrical coordinate problem. So let me describe my region. I go 0 to 2 pi on the, let me just, before I go too far, I'd make sure they didn't say anything else about octants or anything. Oh, hold on just a second. And, hello? All right, continuing on here, I have my restriction on theta, 0 to 2 pi. My radius is bounded between 0 and 2, and my z-coordinates, or z-coordinate is bounded between these two. So the bottom one is x squared plus y squared, and the top is 4. Now, because I'm going to polar, or Cartesian, cylindrical, I'm going to make any conversions, you know, x and y are going to be converted over to polar. So this right here is r squared. So my z is actually going to be between r squared and 4. And I think I should be able to set up this triple integral now. Okay. So this will become 0 to 2 pi, 0 to 2, r squared to 4. Now I'm integrating z, okay? So when we're in cylindrical coordinates, what does z get switched over to? And you have to remember, for cylindrical coordinates, you don't switch z. I mean, if it was x, we would say r cosine theta. If it was y, we would say r sine theta. But if it's z in cylindrical coordinates, it just stays z. So I'm going to leave this as z. But because I'm in cylindrical coordinates, I need an r. And then I can do my dz, dr, d theta. Now I'm going to integrate. So 0 to 2 pi, 0 to 2. Antiderivative of this with respect to z is 1/2 z squared r. Evaluating from z equals r squared to z equals 4 dr d theta, which is equal to the integral from 0 to 2 pi, the integral from 0 to 2. Okay, plug in 4 here for z. 4 squared is 16. Half of 16 is 8, so I get 8r. Minus, now replace z with r squared. Okay, so r squared squared is r to the 4th, times r is r to the 5th. So I get 1/2 r to the 5th. And then dr d theta. Now I'll integrate this with respect to r. So I think I'll do that here. So this equals integral from 0 to 2 pi. Now I'm doing my integration. Antiderivative of 8r with respect to r is 4r squared. And then the antiderivative here, minus 1/12 r to the 6th. And I'm evaluating this from r equals 0 to 2 d theta. And replacing r with 2, I get integral 0 to 2 pi Okay, replacing r with 2, we're going to get something. When we replace r with 0, it's all gone. So I just really need to look at what happens when I replace it with 2. So 2 in here, 2 squared 4, times 4 is 16. All right, what do we got there? I can't do this. That's 64, and then over 12, right? So we can go 4, we can divide by 4, 16 thirds. And then get those together with a common denominator. You know what, I'll just cheat. Okay, antiderivative, I'm just going to do each one separately. I can put my answer together at the end. There's the antiderivative with respect to theta, and I'm going 0 to 2 pi for theta. Okay, when I plug in 0, it's all gone. So I just need to plug 2 pi into that, and that should be my answer. So let's see what we get. 2 pi here, we get 32 pi. 2 pi here, we get minus 32 pi over 3. And I'll multiply, I'll get a common denominator, so I multiply top and bottom here by 3, so I get 96 pi over 3 minus 32 pi over 3, which should give me 64 pi over 3. All right, let's look at number 19. Evaluate the triple integral over E of x plus y plus z dv, where E is the solid in the first octant, so I'm in octant 1. That lies under the paraboloid z equals 4 minus x squared minus y squared. So we're in the first octant. That means that, we have this ground here, the back wall, side wall, we're stuck here. We're underneath this paraboloid. So if I graph that paraboloid at 0, 0, so if I plug in 0 for x, 0 for y, I get 4. So I'm up here at 4. And then it looks like a bowl. Like if I let y be 0, I get x is positive or negative 2. Same thing if I let x be 0. So we've got this bowl, comes down, goes like this. And it goes around, but I'm only in the first octant, so it's like that. So that's my region. And it's kind of something like this. I don't know if you can see that. If I kind of turn it to the side, you can see it like that. I think I kind of over-exaggerated that. Probably be something closer, like whatever. You get the idea. Hopefully that's in the first octant. And so if I'm looking at this solid here, the ground, right? The ground here is going to be that region, but the top of it is actually the paraboloid. So the top of this is z equals 4 minus x squared minus y squared. The bottom of this is z equals 0. And then the region, the projection of that onto the xy plane gives me, let's see, 2 here, 2 here, everything in here. And that's a pretty decent polar region. Let me define my polar region over here. Or actually, I'll put my restrictions on everything over here. I've got thetas between, in this case, 0 and pi over 2. My radius is stuck between 0 and 2. My z value is stuck between 0 and 4 minus this. But remember, this is 4 minus x squared plus y squared. So that's 4 minus r squared. All right, that's going to work out good. I'm in cylindrical, obviously, because this is a polar-looking region. So I should be able to set up my triple. So I should be able to go integral 0 to pi over 2, integral 0 to 2, integral 0 to 4 minus r squared, and then x, sorry, I just erased it, x plus y plus z. Right, so I'm supposed to be integrating x plus y plus z dv, right, over e. And because I'm converting to cylindrical coordinates, x is going to become r cosine theta, y is going to become r sine theta, z never changes in cylindrical, and then I have to have an r from the fact that I'm in cylindrical, and then dz, dr, d theta. So that's the initial setup. And now let me distribute the r through. I'll do that without. I'll just distribute the r through. This becomes r squared. This becomes r squared. And this right here becomes rz. And that's it. And now let me go ahead and do the integration. I'm integrating with respect to z first. So 0 to pi over 2. 0 to 2. Antiderivative of this with respect to z is r squared cosine theta z plus this one r squared sine theta z, and then plus 1/2 rz squared. I'm evaluating this from z equals 0 to z equals 4 minus r squared, dr d theta. All right, well, it's going to be ugly. It's going to be polynomials and stuff. So let's see what happens. This is integral 0 to pi over 2, integral 0 to 2. And now let me replace the z here with 4 minus r squared. So I'm going to have r squared cosine theta times 4 minus r squared. Then I have plus r squared sine theta times this z, which again is 4 minus r squared. And then I have plus 1/2 r times z squared, so 4 minus r squared squared. That's pretty nasty, dr d theta. All right. I think I'm going to try and expand this all out. Let's see. Equals integral 0 to pi over 2, integral 0 to 2. So I'm just doing some algebra here. Distribute this here and distribute this here. So I get 4r squared cosine theta minus r to the 4th cosine theta. And then plus, now distribute this here and here, we get 4r squared sine theta minus r to the 4th sine theta. And then I have to expand this out. So I'm taking 4 minus r squared times itself first. That gives me 16 minus 8r squared plus r to the 4th when I do my expansion and collecting of like terms. And then I have to distribute this through. So I have to multiply this times 1/2 r. So I'm going to get 8r. I'm going to get minus 4r cubed. And I'm going to get plus 1/2 r to the 5th, dr d theta. Antiderivative of this with respect to r. is next. All right, so remember cosine theta is a constant. So antiderivative of this, we get 4/3 r cubed cosine theta minus antiderivative here, 1/5 r to the 5th cosine theta. And then antiderivative here, plus 4/3 r cubed sine theta. Antiderivative here, minus 1/5 r to the 5th sine theta. Plus antiderivative here, 4r squared. Antiderivative here, minus r to the 4th. Antiderivative here, plus 6 times 2 is 12, so 1/12 r to the 6th. Evaluating this from r equals 0 to 2, and then after I'm done with all that, d theta. Well, the good news is that when I plug in 0, everything here is gone. But I've got to plug 2 in. All right, so I think I'll do it up here. So I'm going to plug 2 in, see what I get when I plug in 2. Integral 0 to 2 pi. All right, so I will have 2 cubed is 8, so 8 times 4, 32/3. 32/3 cosine theta. Okay, plug in 2 here, you should get 32 over 5, so minus 32 over 5 cosine theta. And then plug in 2 here, you get 8 times, we kind of did that a second ago, but it's 32/3 sine theta. And then here, this is going to be minus 32/5 sine theta. Here, 4 squared, or 4 times 4 is 16. And then here, minus 16. Nice. And then here, 64 divided by 12. I think we did that earlier. 64 divided by 12 divided by 4. I just can't do simple math, I swear. 12, 32, 6, 16/3. 16/3. I did that earlier, I don't know why. Plus 16/3. Okay, that's what I get when I plug in 2, and then of course when I plug in 0, it's all gone. So all that d theta, these cancel, at least that happens. And I'm just going to go straight through here. I'm not going to try and clean that up. I'm just going to take the antiderivative right now with respect to theta. So this equals antiderivative of cosine theta is sine theta. So I get 32/3 sine theta. Antiderivative, same thing here. So minus 32/5 sine theta. And then antiderivative of sine is negative cosine. So this becomes negative 32/3 cosine theta. And then this one is going to turn that to a positive. So plus 32/5 cosine theta. And then plus antiderivative 16/3 is 16/3 theta, evaluating from theta equals 0 to theta equals 2 pi. All right, let's try plugging in. First, plug in 2 pi. Sine of 2 pi is 0. Sine of 2 pi is 0. Minus cosine of 2 pi is 1. So I get negative 32/3. Again, cosine of 2 pi is 1, so you get plus 32/5. And then plus 16 times 2 pi is 32 pi over 3. Minus, now plug in 0. Sine of 0 is 0. Sine of 0 is 0. Cosine of 0 is 1. So I'm getting negative 32 over 3. Cosine of 0 is 1, so plus 32 fifths. And then 0 here makes it go away. So we have, these are gone. This is negative 32 thirds plus 32 fifths plus 32 pi over 3. And then distribute negative through, so plus 32 thirds minus 32 fifths. That does not look right. These look like they cancel. And those look like they cancel. Okay, hold on. Somewhere I switched that to pi, that was supposed to be pi over 2. Okay, I can change this quickly. That would be the answer, but we're going to pi over 2. Look back in the video, somewhere in there I switched over. I know I put pi over 2 initially. Okay, this will work. All right. Sine of pi over 2 is 1, so we get 32 thirds minus sine of pi over 2 is 1, so 32 fifths. Cosine of pi over 2 is 0. Cosine of pi over 2 is 0. Plug in pi over 2 right here. You get 16 times pi over 2 is 8 pi over 3. Then minus, when we plug in 0, well, I just did that. Sine of 0 was 0. That was 0. This was negative 32 thirds, and then plus 32 fifths. And yeah, things are a little bit different here. As you can see, 32 thirds minus 32 fifths plus 8 pi over 3 plus 32 thirds minus 32 fifths. So I don't believe we get any canceling on those now. So we get 8 pi over 3, that's this. Now put these two together. So 64, so plus 64 thirds, and then put these two together, minus 64 fifths. And then we get a common denominator between the two of those. So if we get a common denominator between these two, I have to multiply top and bottom here by 5. So 64 times 5, 20, 232. So this is 320 over 15 minus now 64 times 3, right? Because I've multiplied top and bottom there by 3. So 12, 18, 19, 192. 192 over 15. And when you subtract 128, I believe you get 128 over 15. Plus 128 over 15. There we go. All right, sorry about that, pi over 2. All right, that's it for that section.